measurement of probability greatly depends on mutually exclusive and mutually independent events. Mutually exclusive events are those that cannot occur simultaneously, or you can say that they cannot occur at the same time. For example, there are certain real-life processes like in finance and business management where you come across with budgeting and management processes. For example, if there are limited investment opportunities, then some of the opportunities may not be employed together and they are considered as mutually exclusive. Mutually exclusive events are sometimes confused with independent events. While there is a big difference, the independent events are those that may occur at the same time. They just are not affecting each other's probabilities. Excuse me. The outcome probability of one event has nothing to do with the outcome probability of the other event, and it would be easier to understand independent events if you consider dependent events. And dependent events, as we say, depend on what happened before. So for example, you may have a deck of cards and you take one card out of the deck of cards and then you do not replace it and you take another card. Then the choice of the second card will depend on that it has not been chosen before. Or illegal parking followed by a parking ticket. They are all dependent events. While independent events have nothing to do with the other event's chance of happening or not happening, and for example, keeping a pet and bringing groceries. They are two independent events. Today we will discuss mathematical representation of independent and mutually exclusive events and how we can compute the probabilities of such events that depend on certain conditions. So bear with me. Firstly, we are talking about mutually exclusive events. This is a very specific term in statistics, which means that if two events A and B can occur exclusive of each other and they cannot occur at the same time, then they will be called mutually exclusive. And this also means that A and B will not share any outcomes and their intersection will be an empty set. And so the probability of intersection would be 0. A very simple example could be walking backward and forwards. You cannot do that at the same time. So walking forward and backward can be considered as two events that are mutually exclusive. Now we see a mathematical example to understand it better. So we are considering a sample space S consisting of first 10 elements and 3 subsets of S as A, B, and C, where A has first 5 elements of S, B has elements 4 to 8 from S, and C has elements 7 and 9. You can see that A and B have some elements in common. Can you? Yeah, you can see that they have 4 and 5 as common elements. So A intersection B is non-empty. While A and C do not have anything in common, and A intersection C would be an empty set. And so the probability of A intersection will be a number which is 2 out of 10 because A intersection B has 2 elements out of 10 elements of the sample space, and therefore A and B are not mutually exclusive while A intersection is empty, so the probability of A intersection C is 0 and A and C are mutually exclusive events. Now it may happen that you come across with two events that you don't know about if they are mutually exclusive or not. In that case, please consider them not mutually exclusive until you have a clear evidence that they are exclusive events. To understand better about the mutually exclusive and the mutually non-exclusive events, let's conduct a simple experiment, and I want you to do that experiment for me. So please take 2 fair coins and flip them together. What do you expect to see? Do you expect to see 2 heads? No, you expect to see more. You may have 2 heads, you may have 2 tails, or you may have a head and a tail on each of the coins. Okay, so how many outcomes are there? There are 4 outcomes. So the sample space would be consisting of these 4 outcomes. And next we consider an event A of getting at most one tail. What do you expect to see in at most one tail? It should be either one tail out of two, or there should be no tail. So which outcomes of the sample space represent events that have at most one tail, which means no tail or one tail? You can pick HH, you can pick HT, and you can pick TH. TT would be excluded because it has two tails. So A has three elements, and if we consider another event B that gets all tails, only tails, then obviously B has only one element, TT. And can you see the difference between A and B? Can you compare them? Can you see if they share anything or they do not share anything? Yes, you can see that actually B is the complement of A, because the elements of B are not in A and the elements of A are not in B, so B and A both are complements of each other. You can write B equals A prime. And so the probability of A added to the probability of B can yield probability of A plus probability of A prime, and we know from previous lectures then this is always equal to 1. And next we see that the probabilities for events A and B are respectively 3/4 and 1/4. And we are now considering an element C that consists of all heads. What do you expect in C if it has all heads? Obviously you will be expecting only one element in C, which is HH, no tails. Alright, so if C has all heads, then what do you think about B and C? B has all tails, C has all heads. Do you think that they are mutually exclusive events? I think you do, because the probability of B intersection C is 0, and so B and C are mutually exclusive events. While if you consider the events A and C, then they do share something in common, which is HH, and therefore A intersection C would be non-empty and they will not be mutually exclusive. And now we see what we mean by mutually independent events. And please bear in mind that independent and mutually exclusive are not the same thing. They are two different things. Two events being mutually exclusive means that their intersection is an empty set, if you remember. And their probability of their intersection would be 0. But if two events are mutually independent, then this would mean the occurrence of one will not affect the occurrence of other. So the probability of an event A, given that B has occurred, would mean probability of A itself, because B has occurred independent of A. And similarly, A has occurred independent of B, so the probability of B given A would be the probability of B itself. It can also be said in another way that the probability of A intersection B would be the probability of A times the probability of B. So the intersection is non-empty. And the intersection probability of the intersection is not 0. And it is also true for independent events that if you do not know that two events A and B are independent, consider them as dependent unless it is proved that they are independent. A very simple example of understanding the independence of two events is related to the example we just studied, where we tossed two fair coins together. Now, instead of that, if we toss one coin twice, then it is a different event. And the tossing of the coin for the first time has no effect on the tossing for the second time. These two are mutually independent events. So mathematically, the above three statements are the same. And to prove if two events are mutually independent, you have to prove only one of the three statements because they all mean the same thing. So if you can prove just one statement, that would prove that they are independent. And if they are not independent, then we say that the events are dependent. We're also considering constructing sample spaces here with two different options. So the sample spaces can be considered by replacing one of the outcome or without replacing the outcome. So for example, if each member of a population is replaced after it is picked, then there's a possibility that they can be chosen more than once, that same element. And in that case, the events are considered to be independent because the replacement means that you can choose the replaced element again. So the chance of first pick will not change the chance of the second pick. While if you do not replace an element chosen, then each member of a population may be chosen only once. And in that case, the probabilities of the second pick are definitely affected by the result of the first pick. And so the events are considered to be dependent. Now let's do an example and experiment together. And the experiment will be done with the help of a deck of 52 cards. You know, there are 52 cards in a deck of cards, and there are 4 suites in it. And these suites are clubs, diamonds, hearts, and spades. And each suite consists of 13 cards. The numbers from 1 to 10, and then there's a jack, there's a queen, and there's a king. Now to start the experiment, just pick 3 cards at random. Now suppose that you have the 3 cards as Queen of Spades, King of Hearts, and Queen of Spades. Can you identify or decide if the sampling was done with or without replacement? So you picked the Queen of Spades, and then you picked the King of Hearts, and then you picked the Queen of Spades. So can you decide if the sampling was done with replacement or without replacement? So once a card chosen was replaced or not? I'm sure your answer is that the sampling was done with replacement, otherwise the Queen of Spades could not have been chosen again. There's only one way of choosing the Queen of Spades for the second time, that the first time it was chosen, it was replaced back, because there's only one Queen of Spades. Okay, so we click that the sampling was done with replacement. Okay, next, suppose you pick the Queen of Spades, and then King of Hearts, and then Jack of Spades. What do you think in that case? If the sampling was done with or without replacement? For that you have to think that once you pick the Queen of Spades, was it necessary to replace the Queen back to choose King of Hearts? It wasn't. So the King of Hearts may have been chosen without replacing the Queen or with replacing the Queen. Similarly, the Jack of Spades could have been chosen without replacing the King of Hearts and Queen of Spades, or with replacement as well. So in this case, your answer should be that they can be chosen either without or with replacement, so it cannot be determined if the sampling was done with or without replacement. And now we see how did we do in this case. So our answer is correct. Both of our answers are correct. Now we see an example of another fair, well-shuffled deck of 52 cards, in which you have to make a choice of 4 cards. And for that choice of 4 cards, you have to consider both possibilities. In the first possibility, you are considering that the 4 cards are chosen without replacement. So once a card is chosen, you cannot replace it back. The second card has to be chosen without replacing the first card. So in that case, can you decide which of the following choices are possible? Which means that in the first choice, You are picking 3 of a spade, 3 of a heart, 3 of a diamond, and then 3 of a club. Is that possible? Yes, that is definitely possible, because they all are different and none of them is repeating. So the first case is possible. Similarly, the second case are all different. That's all possible. But in the third case, once you choose Jack of the Heart in the second as a second card, you cannot choose it as the fourth card. So this choice is not possible. Similarly, in the fourth case, if you choose the King of Heart in the first place, you cannot choose it again in the fourth place. That's also not possible. But the fifth case, it has no repetition, so that's also possible. Now, in the second case, you again choose 4 cards with replacement. So once you choose a card, you can put it back into the deck and then choose another card. So this means that in this case, all repetitions are possible. So maybe we should simply click all of them without thinking, because we know that all possibilities are counted, and we see how did we do. And we see that both of our choices are green, which means we made the right choices. In this example, we draw 2 cards from a standard deck of 52 cards with replacement, which means that we draw 1 card and then we put it back and then we draw another card. And we want a probability of getting at most 1 black card, which means that we want the probability that we get either no black card or 1 black card, not more than 1 black card. So this is what we mean by at most 1 black card. The first step would be to form the sample space. So let's go back to our worksheet and see what sample space we get out of the experiment. Okay, so what we see here in the first possibility, when we pick first card, is that it may be black or it may not be black. So let's call the first possibility as B and the second possibility as N. Okay, so if the first possibility is a B, we get a black card. Then there are 2 further possibilities, which are that it could be a black card again, or it could not be a black card. And the same possibilities occur for N. So if we don't have a black card in the first go, it could be a black card in the second go, or it could not be a black card in the second go. So the sample space comes out to be 4 pairs that we just have in the tree. Okay, and now we see that since we have to get at most 1 black card, the possibilities of BN and NB are always there. They are the possible outcomes. But we have to decide between 2 outcomes, BB and NN. Whether BB is an outcome? Obviously not, because we have to have at most 1 black card. So black card after black card is not an option. And N followed by N is definitely an option, because we may not have a black card. So in this way, our possibilities turn out to be 3 out of 4 for getting at most 1 black card. And we pick out all the possibilities that may have according to the requirement of the question. So we go back to our question and enter our answer as 3 by 4 and see how we go. Okay, our answer is correct. In this example, we consider a student that goes to the library and chooses a book or a DVD or both. And the probability that they choose a book is 0.3. The probability that they choose a DVD is 0.2, and the probability that they choose both a book and a DVD is 0.06. And we are interested in first finding the conditional probability B given D, which means that the probability of choosing a book when a DVD has already been chosen. So let's go to the worksheet and work it out. Now we know that the book and the DVD has an equal chance of being chosen. So we first draw the T diagram for choosing a book and a DVD, followed by choosing another book or another DVD. and we see that there are 4 branches of this tree diagram, and a book can be followed by a book or by a DVD, and similarly a DVD can be followed by choosing a book or another DVD. So we are interested in first finding probability of D given B that a book is chosen when the DVD has already been chosen, which is the third option. And we see that in this case we want to find probability of B given D, and this is equal to the probability of the intersection divided by the probability of D. And all these values are given to us, and we know that the probability of choosing B and D, which is the probability of B intersection D, is given to be 0.06, and the probability of choosing a DVD is given to be 0.2. So the probability comes out to be 6 on 20. So we go back to the worksheet and enter the value. So you can write 6 on 20, or you may simplify it and write by 3 by 10. That also should be correct. And the next question to be answered is the probability of B given B. So the probability of choosing a DVD when the book has already been chosen. So to answer the next question, we have to find probability of D given B, which should be again the intersection of D and B divided by the probability of B this time, because the condition is that B must have occurred. And we know that the probability of the intersection is as before 0.06, and the probability of choosing a book is 0.3. So it turns out to be 6 on 30 or 1 on 5. Okay. So we enter 1 on 5 here for the probability of D given B has occurred. Okay. Now the next 2 questions to answer are whether the events B and D are independent, or they are mutually exclusive, or they are both, or they are not any of these. So we go back and check first with our worksheet if B and D are independent events. And for that we need to satisfy a certain condition. If you remember that for 2 events to be independent, we need to check if their conditional probability is equal to one of them, the probability of one of them. And in this case that would be to prove that the probability of D given B equals probability of D, which means that we have to check the probability of D given B, which is 1 on 5, while the probability of D is 0.2. Are they equal? Of course they are. We know that 1 on 5 is the same as 0.2. So the answer is yes. And the next question was whether D and B are mutually exclusive. So we need to check their mutual exclusiveness, and for that we need to satisfy the condition that the probability of D intersection B is 0. And do we have that? Of course not. First question is yes, and the second question was no. So now we check how we have performed. Okay, so it looks like all our answers are correct.